start recording here. We are going to do section 4.7, and so section 4.7 is what is called inverse trigonometric functions. Okay, so we're used to taking the sine or the cosine or the tangent of a certain angle, right? So like we might be able to say, find the sine of pi over 4. So anybody remember what the sine of pi over 4 is? Okay, root 2 over 2, right? So that's going kind of the forward direction. That's what we've been doing all semester long so far. But today what we're going to do is we're going to actually work on going the backwards direction. So today we're going to work to answer the question, right? The sine of what angle is root 2 over 2, right? So if we know that the sine of pi over 4 is root 2 over 2, then we could say the sine of what angle is root 2 over 2? Oh, well, that's what we just knew before as pi over 4. So we're going to kind of go backwards. And that going backwards is basically taking an inverse. It's kind of like when you square something. To undo a square, you can take a square root. So it gets you back to where you started. So this is the same thing. We have inverse functions for each of the trig functions. So, and part of that is because it's kind of tedious to write out this whole statement, right? So I'd like a nice kind of short mathematical way to write the statement. What is the sine of what angle is root 2 over 2? Okay, so before we can do that, so we're going to go through, there are 6 inverse trig functions. We're going to talk about each one of them. But before we do that, does anybody remember from Math 126, what has to happen for you even to have an inverse of a function? So back in Math 126, we should have learned that not every single function has an inverse. And so something has to be satisfied to be able to find an inverse. So does anybody happen to have a guess or remember what that was? Okay, no clue. That's okay. All right. So does this ring a bell for everyone? The horizontal line test. The function has to be 1 to 1. It has to pass the horizontal line test to have an inverse. And remember, when you find inverses, you swap the x and the y, right? So to have an inverse, a function must be 1 to 1, i.e. pass the horizontal line test. Okay, so if we look at the function, if we look at y equals sine x, right? So we talked before, so we've been used to just drawing one period of y equals sine x. But remember, y equals sine x goes on and on and on forever, right? In both directions. And just to kind of label a couple of the points, right? Out this way, this was 2 pi, this was pi, this was pi over 2, this was 3 pi over 2. It's 1 high, 1 low, and then I could also label these minus pi over 2, minus pi, minus 3 pi over 2, minus 2 pi. Okay, so it's not like a perfectly drawn sine curve, but it's pretty decent there. And so if I go to do the horizontal line test, so remember the horizontal line test to see if something is 1 to 1 means when you draw horizontal lines, the horizontal line can only cross the graph once. So if I draw a horizontal line here, is it crossing my graph only once? No. Yeah, it's crossing my graph more than once, right? It's definitely not just one time. Okay, So that presents a little bit of a problem, right? Because I want to find the inverse, but I want there to be an inverse, but the only way there's an inverse is if I have a function that is 1-to-1. So what we do for the trig functions is something a little bit special. And what that is we actually chunk off a part of the sine graph. So we look at this part between minus pi over 2 and pi over 2. And that's the only part we worry about. Remember the sine graph, that little part, like the sine graph repeats itself. So I don't have to worry about the whole entire graph. So we define the inverse sine we only worry about it on the interval from minus pi over 2 to pi over 2. So the inverse sine, so y equals sine negative 1x. Or another way you could write this is y equals arc sine of x. Alex uses both. So they use the -1 notation, and they also use the arc sine. Some textbooks exclusively use the arc sine notation. And the reason they do that is because people often get confused about the -1. So a really important side note is when we're dealing with trig functions, sine inverse x, so this is not equal to 1 over the sine of x. Okay, I know we're used to the -1 power, meaning 1 over, but this is like an abusive notation that mathematicians use, and so we don't use the -1 power with a trig function as in that shortcut by sticking it between the trig and the x. So if you see a sine and then the -1, they're talking about the inverse function. So this is, if you wanted to do 1 over the sine of x, you would write it as sine of x all to the -1 power. That's going to end up being 1 over sine x. But when that -1 is between the sine and the x, in our notation, they're talking about the inverse function. So just kind of keep that in mind. So we have y equals the inverse sine of x, or y equals the arc sine of x. And the way that it looks like, so if you remember, when you're doing inverses, you swap x and y. So everything that was an x becomes a y, everything that was a y becomes an x. So if I do that with this graph, what's going to happen is, if you look at this pink part here went between minus pi over 2 and pi over 2 in terms of the x's, which means now on the y's, it's going to go from minus pi over 2 to pi over 2 on the y's. And then on the x's here, it went between, not on the x's, on the y's on the original graph, it went between -1 and 1, which means on the graph here, it's going to go between -1 and 1. And so it looks roughly like this. And so the domain of the inverse sine function is going to be from -1 to 1. And the range, which means the answers we get out, have to be between minus pi over 2 and pi over 2. And that's telling us that we're in quadrant 1, or minus pi over 2, remember you go down, so minus pi over 2 is actually quadrant 4. So basically what we're doing when we're dealing with an inverse sine function is we're looking for answers from quadrant 1 or quadrant 4. So I know that was like a lot of information, and you're probably kind of like, I still don't exactly know what's going on. So what we're going to do is we're going to do some examples. So I can totally answer that. Give me 1 second, Liana. So we're going to do some examples, and then we'll go back and define all the other inverse trig functions. So I chose the area between minus pi over 2 and pi over 2 for a couple of reasons. So the most important reason is, if you notice, if I go between minus pi over 2 and pi over 2, it corresponds to every single value between y value between -1 and 1. So I've gotten every single y value going on here. And since I've gotten every single y value going on here, that makes it so that I can find all of the, I can find values for all of the inverse functions. So that's kind of the first thing. The second thing is that I could pick any piece of the sine function that I wanted where it covered everything. So like, for instance, I could have, if I had wanted to, I could have taken, say, oh, well, let's take the piece between -3π/2 and pi. That takes care of the top stuff. And then maybe I'll take the piece between pi and 3π/2. So I could have taken those two. Because together, those would cover all of the values between -1 and 1 on the y. I could have even said, no, let's go over here from 3π/2 and we'll keep going up here to this part, right? So there's lots of different little pieces of the sine graph that I could have picked, but we mathematicians have kind of chosen and said, look, the standard part that we're going to pick is -π/2 to π/2. Does that help? No problem. Other questions? No. Why did I write Q? Okay, so I wrote quadrant 1 and quadrant 4 because the range, if you're going from here, my range is from -π/2 and from -π/2 to π/2. So if we think about the unit circle, right? So here's the unit circle. So -π/2 is down here, right? It's going this direction. So -π/2. π/2 is here. So basically we're looking for angles that are in quadrant 1 and quadrant 4. Does that help with that question, Brendan? Yeah, so the graph is the inverse. Yeah, this graph that I drew down here, this is y equals the inverse sine of x. Other questions before we do a couple examples, and then we'll come back and we'll do the same thing. We'll talk about cosine and tangent and the other ones. Would that mean y equals sine x is quadrant 3 and 4? So it means quadrant 1 and 4, not 3 and 4. I think that answer about what quadrants and stuff might make sense in a minute when I do some actual examples. So let me do some examples. Is everyone okay if I go to the next page? I just don't want to go to the next page if people are still trying to write. Okay. So, first off, one of the most helpful things in doing these problems is if you have a unit circle close by. So I'm going to add in a unit circle here so that we can use this. Okay. So, evaluate. A. The inverse sine of 1. Okay, so when we are talking about the inverse sine of 1, so what we're saying is, so when we think about inverse functions, we want to think about what it means, right? So whenever I see an inverse function, I always change it into just either the right, like if it's an inverse sine, I'm going to change it into dealing with a sine function. So basically what I'm saying is that the inverse sine of 1, my answer is going to be an angle. Because remember what this is saying what angle has a sine value of 1, right? So that's what that original problem is asking me. It's asking me what angle has a sine value of 1. So anytime I have an inverse function, I always set it equal to an angle. So I've got the inverse sine of 1 is equal to this angle theta. And then what that does is that allows me to rewrite the problem. So what I'm saying is that the sine of theta turns out to be equal to 1. Right? So I've basically just taken the problem and I've restated it in a slightly different way. Does anyone have any questions on what I did there? No. Okay. So the next thing I'm going to do is now I'm going to go to, so when we're talking about the sine, so when we've been doing the sine in terms of looking at the unit circle, the sine value we found by looking at what? The x, the y, did we divide them? Like how did we find the sines? Okay, so we found the sines by looking at the y. So we're looking for places where the y value is equal to 1. Okay, so the sine of theta, so all I did here is basically, so I had a couple of people ask me how did I go from this first line to the second line? So this is that's the definition. When I have an inverse sine, what I'm doing is it's basically saying that that's equal to some angle. And this is asking me the question, the sine of that angle is equal to 1. The other way you could think about it, let me move this down a little bit, is you could think about it, it's almost like I had this. So I had the inverse sine of 1 being equal to, I'm going to leave some space, theta. And then what I did was I took the sine of both sides. So I took the sine of the inverse sine and I took the sine of theta. A sine and an inverse sine almost all the time will cancel each other out. So we're going to be a little careful because we're going to talk about this like towards either the end of class today or next class. But essentially a function and an inverse function undoes each other. And so these in a sort of way cancel each other out. And that's sort of where I'm getting the sine of theta equals 1. But really the bigger thing is to basically recognize that when I have this, the inverse sine of 1, it's asking this question, what angle has a sine value of 1? And that's the same as rewriting it as the sine of theta equals 1. Does that help for the people who asked me that question? Okay, so the negative 1 it's not a part of the problem. This sign with the negative 1 is a notation. This is the notation we use for the inverse sine. So this whole entire part here, this sine negative 1, all this is saying is inverse sine. So this is saying the inverse sine of, and then whatever our value is. So it's saying the inverse sine of 1. So in this case, negative 1 is not, it's not a number, it's a notation. And I know that's kind of confusing. That's why some books, rather than write the sine negative 1, they'll write the problem this way, arc sine of 1. And that's the same thing. So if you see arc sine of 1, we're doing the same thing. We're saying that equal to theta, and we're saying, okay, this is saying that the sine of theta is equal to 1. Does that help? Great. Okay, so somebody said pi over 2. Yes. So now what we're doing is we're looking for where the sine is equal to 1. So remember, the sine is the y value, and our y value is equal to 1 here, and so that's going to be pi over 2. So in this case, the answer is going to be pi over 2, because that's where that statement is true, where the sine of theta is equal to 1. So let's try another one. So what about B, the inverse sine of root 3 over 2? Oops. Okay, so I have a problem, inverse sine of root 3 over 2. So again, I can think of this is equal to some angle. And then we're saying, okay, the sine of that angle is equal to root 3 over 2. So again, sine is the y value. So if I'm looking on the unit circle, where is the y value equal to root 3 over 2? Okay, pi over 3. And is that the only place? Okay, so somebody else said, well, it also happens at 2 pi over 3. So the sine is equal to root 3 over 2 here, but it also happens to be here. So this is why, right, at the beginning we restricted where we were looking, and I said we're only looking in quadrants 1 and 4, because otherwise you get two answers, and it's not a good thing when you have a function. You can't ever get two answers out of a function. So I think of a function like a machine. You put in an input, it does something, it spits out one answer, right? It's not good if you put in an input and it goes, well, it could be this or this, right? That's not very clear. So we want our inverse to be a function, which is why we restrict ourselves at the beginning. So we are only ever going to, when we're dealing with inverse sine, okay, we're going to talk about the other ones, but for inverse sine, we're not ever going to look at this side, right? If you notice the values, all the values on this side, right, they all have a mirror on this side. So we don't have to worry about the values over here, we just have to worry about the values over here. So I have a couple of people asking me, well, what about if you wrote the answer in degrees? So it's kind of the convention that pretty much for the rest of Math 127, we work in radians. So if you're just given the inverse sine of root 3 over 2, unless the problem specifically asks you to give it in degrees, we're always going to give it in radians. So everything we're going to do is pretty much going to be radians unless a problem specifically said use degrees. There is one little exception to that, and that's when we get to some word problems, but we're not there yet. That's after the next test. Other questions? Okay, so because we're not looking at that left-hand side, in this case, our answer will just be that pi over 3. Okay, one other little kind of slight catch to things. So remember how I said that the range for the inverse sine function was from minus pi over 2 to pi over 2, right? And we said how that corresponds to quadrant 1, and it also corresponds to quadrant 4, so that's why I crossed out that left-hand side. If you notice these angles here, right, they're written like I started here and I went all the way around this way. But we were trying to go to minus pi over 2, so we were trying to swing this way. So we have to think of all of these angles in this fourth quadrant as negative angles. So while this angle here is 3 pi over 2, it's also the same as minus pi over 2 if I swing in the negative direction. So we have to think about swinging each of these in the negative direction. In the negative direction, all they are is the mirror image of what this angle is, but with a negative. So 5 pi over 3, this is the same as minus pi over 3. 7 pi over 4 is the same as minus pi over 4. 11 pi over 6 is the same as minus pi over 6. So when we give answers in the fourth quadrant, when we're dealing with inverse functions, so this is the only time, fourth quadrant problems, inverse functions, you have to write the answer as a negative angle. So for instance, if I asked for the inverse sine of negative 1/2, right? So that would be here, right? There's my y value of minus 1/2. So rather than write 11 pi over 6, we're going to write minus pi over 6. So same deal, this is saying equals theta, so we're looking for when is the sine of theta equal to minus 1/2. We would have said 11 pi over 6 in quadrant 4, but we have to write it as the negative, so it's going to be minus pi over 6. Questions? So there's a little bit of a tricky thing when you're dealing with quadrant 4. Correct. It's only like that in quadrant 4. Yep. Other questions? No. So while other times you can add, like, so if you added 2 pi to make it positive, that'll bring you back to 11 pi over 6. And the problem with that is that 11 pi over 6 is not in this range. So we define the range of the inverse sine function to be from minus pi over 2 to pi over 2. We restricted and took this chunk of the sine function. So since we're only dealing with this chunk, our angles have to be values between minus pi over 2 and pi over 2. So they have to fall in that range. And while if you added 2 pi and got 11 pi over 6, you would have an angle that gives you the correct sine value. It's not in this range. So when you're dealing with an inverse function in quadrant 4, you have to rewrite it as a negative. Does that help? No problem. Other questions? No. Okay. So we're going to make a chart that kind of shows all the stuff about the different inverse trig functions, so that then we can worry about, we're going to make a chart for sine, cosine, and tangent. Excuse me, so that then we can write these things down and practice these. So. Okay. So when we have, so we're going to talk about our function. We're going to talk about the graph. We're going to do the domain, the range, and what quadrants we're looking in. Okay, so that first one is the one we just did, which is y equals the inverse sine of x, or you could see it written as y equals arc sine of x. The graph is what I showed before, right? It looks like this, where this is minus 1, this is 1, it's pi over 2 high, and minus pi over 2 low. Is that? So that's what we had before. And we said the domain here. So the domain remembers your x's. So the domain here is from minus 1 to 1. The range, which we talked about, where we're restricting it, is from minus pi. Whoops. What did I do there? Minus pi over 2 to pi over 2. And we said that's quadrant 1 and 4. I like to put a little asterisk next to my quadrant 4 to remind myself that when I find those values, I have to make them negative. So when I'm in quadrant 4, that's when I have to do that negative part. So I kind of always put a little asterisk next to quadrant 4 just to try to remind myself of that. So that's the one we did before. Inverse cosine is pretty similar. So y equals cosine inverse of x. Or another way to write it is y equals arc cosine x. The graph here, so it's still between -1 and 1, but in this case, we actually go as high as pi. And so it actually looks like this. So it looks pretty similar to the inverse sine graph, but it's kind of going a slightly different direction. And the domain is still -1 to 1. But the range here is from 0 to pi. And if we're talking about we're going from 0 to pi, which quadrants are we dealing with? Yeah, 1 and 2. So the answers we're going to look for in terms of inverse cosine problems are going to be quadrants 1 and quadrants 2. Questions? No? Okay. The next one we're going to look at is y equals the inverse tangent of x, or y equals arc tan x. And so the inverse tangent of x, so remember the tangent graph had asymptotes, and those asymptotes were at intervals of pi over 2. And so rather than having vertical asymptotes, so remember when we do inverses, we're swapping the x and the y. So we had these vertical asymptotes. So when we swap x and y, things that were vertical now become horizontal. So we're going to have horizontal asymptotes here. And so our function looks like this. And this is pi over 2, and this is minus pi over 2. So the domain here is from minus infinity to infinity. I can put anything I want into the inverse tangent function. But the stuff I get out is minus pi over 2 to pi over 2. And I don't have the square brackets because we never quite get to the minus pi over 2 and the pi over 2. We get really close, but we just don't quite get there. And again, just like the inverse sine, this is coming from quadrants 1 and 4. And again, when we're in quadrant 4, we have to put that asterisk. Questions so far? Okay, so again, there's a star next to quadrant 4 because when we're in quadrant 4, it's just to remind myself that we can put a little note. So the star means right as a negative angle. Right, as a negative angle. So anything basically whenever we're in quadrant 4, we have to rewrite our angle as a negative angle. Other questions? No. Okay, so for inverse cosecant, inverse secant, inverse cotangent, we're not going to worry about the graphs of them. Because they don't come up all that often. We're mostly dealing with inverse sine, inverse cosine, inverse tangent. So we're just going to write down what the domain, the range, and where those quadrants are. We will do problems with them, but we're not going to worry about the graphs of those. So if you have y equals the inverse cosecant of x, or y equals the arc cosecant of x. Okay, so remember when we did cosecants and secants, those were the graphs that were those U's, and they kind of moved up and down. And so they came in pieces. They had asymptotes. And because of that, our domain ends up having asymptotes, or our domain and our ranges end up coming in chunks, in pieces. So the domain is from minus infinity to negative 1, union 1 to infinity. And the range on the inverse cosecant is from minus pi over 2 to 0, union 0 to pi over 2. So this is another one that's using quadrants 1 and 4. And again, we're using quadrant 4 as that negative quadrant. So we have to write those answers as a negative. Questions about that? No? Oops. I want to stay on this page. I just want to move this up a little bit here. Okay. So if y is equal to the inverse secant of x, or y equals arc secant x, then we're talking about here, the domain is going to be from minus infinity to negative 1 again, union, again, 1 to infinity. The range here is from 0 to pi over 2, union pi over 2 to pi. And so this is, again, quadrants 1 and 2. And then finally, the y equals the inverse cotangent of x, or y is equal to arc cotangent x. So this would be, the domain is from minus infinity to infinity, and the range is from 0 to pi. And so this too is quadrants 1 and 2. Questions? No. Okay. So now that we have this kind of all out, the thing to kind of like notice is that it's basically the ones that are you're either at 1 and 2 or 1 and 4. So the things that are 1 and 4 are the inverse sine, inverse tangent, and inverse cosecant. So that's kind of a good way to kind of try to remember those. Is everybody okay if I go to the next page? Okay. No one's telling me to wait, so I'm going to guess. Okay. All right, so let me put that unit circle here back in, just so we can reference it. All right, so evaluate. A. Inverse cosine of 1/2. Okay, so inverse cosine, right? So cosine, we're looking for the x or the y values. Yeah, so for cosine, we're looking for the x values. So we're trying to see we're basically saying, okay, the inverse cosine, or the inverse cosine of 1/2. So if we think about this being equal to theta, we're saying, oh, the cosine of theta is equal to 1/2, right? And so we're looking for where is the x value equal to 1/2. And remember, inverse cosine is here in quadrant 1, right? We're either here in quadrant 1 or here in quadrant 2. So we're looking for where is the x value equal to positive 1/2. It's equal to positive 1/2 at pi over 3. So the answer here is pi over 3. B. So inverse sine of 0. So again, remember we're looking for an angle. So we're saying the inverse sine of some of 0 is going to be equal to some angle theta. So we're saying the sine of theta equals 0. Remember, inverse sine, we're looking in the first quadrant or the fourth quadrant. But remember, when we're down here in the fourth quadrant, I'm putting that little asterisk because we have to take the negative angles. So in this case, we're looking for when is the sine equal to 0. And as Liana said, that happens when we're at 0 radians, right? So our answer in this case is 0. Okay, C. So we're looking for the inverse secant of root 2. So again, remember inverse secant equals some angle theta. So we're looking for when is the secant of theta equal to the square root of 2. So this is where it could be helpful if you remember that secant is 1 over the cosine, right? So if the secant of theta is equal to root 2, we're looking for where the cosine of theta is equal to 1 over root 2. And you might go, well, Dr. Gorman, there's no place on the unit circle where I have 1 over root 2. And I would say that's true, sort of, right? I don't have something written on the unit circle that is exactly 1 over root 2. But if I were to multiply the top and bottom here, if I were to rationalize this by multiplying by root 2 over root 2, this would actually end up being root 2 over 2. And so there is places where the cosine is equal to root 2 over 2. So what angle gives us the cosine equal to root 2 over 2? Yeah, pi over 4. Questions? No? Okay. So let's try another one here. So D, what about the inverse sine of minus root 2 over 2? So again, if this is equal to some angle theta, we're saying that the sine, I don't know what keeps happening. I think I keep like leaning on the, so the sine of theta is equal to minus root 2 over 2. So when does that happen? Yeah, and good job. I didn't trip you up. You guys didn't tell me 7 pi over 4. So it does happen down there at 7 pi over 4, but remember we have to write them as a negative. So exactly, the answer here is minus pi over 4. All right, so let's try another one, E. So what about the inverse? So we'll do a tangent. Inverse tangent of negative 1. Okay, so it's not 7 pi over 4 for the following reason. So I had a couple people ask me, why is it not 7 pi over 4? So it is this place, right? I'm here. This is where the sine is minus root 2 over 2. However, to get to 7 pi over 4, you have to start here and rotate around this way. So that's what gets us to 7 pi over 4. We're starting at 0 and we're rotating in the counterclockwise direction. When we're dealing with inverse trig functions, and we're dealing with stuff in quadrant 4, rather than rotate the way I rotated there in blue in the counterclockwise direction, we want to rotate this way as a negative angle. So the blue part here is 7 pi over 4, but instead we want to write it as rotating a negative angle. And so it's going to be negative pi over 4. Since all the other part is 7 pi over 4, I have just another little pi over 4 to get back to the beginning. So we're rotating that negative pi over 4. So we're getting to the exact same place. It's just we have to write it slightly different. It's kind of like, in some sense, it's almost sort of like a nickname, right? Like, so my full name is Jennifer, but I go by Jen. So like the formal name of that angle is 7 pi over 4, but its nickname is minus pi over 4. Does that help? And this is you only have to do this when you're dealing with inverse functions and you're dealing with things in quadrant 4. So inverse functions in quadrant 4, you have to write them as a negative angle. Okay, so back to my tangent problem here. So the inverse tangent of negative 1, so this is going to be equal to theta. So we're saying that the tangent of theta has to be equal to negative 1. So when is the tangent equal to negative 1? And remember, the inverse tangent is defined in quadrant 1 and in quadrant 4. So we're looking in one of these two places. Okay, so pi over 4, it would be a positive 1. We're looking for the negative. Yeah, so negative pi over 4. So we happen to be actually at this exact same place again. So here's the thing. People might go, oh, how did you figure that out? If you want to, you could go through and divide each one of these to be able to figure out what the tangent value is, right? So if I take, this pi over 2 over pi minus if I take square root 2 over 2, comma, minus root 2 over 2, remember the tangent is y over x, so it would be minus root 2 over 2 all divided by minus root 2 over 2. And so that's going to just end up being, the x is positive. That's going to end up being -1. So if you're dealing with inverse tangent or inverse sine, you have to look in quadrants 1 and 4, or inverse secant. So inverse sine, inverse tangent, inverse secant, you're looking, or not secant, sorry, inverse sine, inverse tangent, inverse cosecant, we're looking in quadrants 1 and 4. Inverse cosine, inverse cotangent, inverse secant, we're looking in quadrants 1 and 2. So that's what on this last page, that's why I put this chart, right? So this chart shows you exactly where you're looking depending on which function you're dealing with. Does that help? Maybe. Okay, so what I was saying is that if you want to go through your unit circle and do all those divisions, right, like we could divide this one here and say, oh, this one, to figure out what the tangent would be, is going to be minus root 3 over 2 divided by 1/2. So if I do that, keep, change, flip, it'd be minus root 3 over 2 times 2 over 1. So the 2's would cancel. So at this point here, the tangent is minus root 3, right? You could divide this one, right? So at this point here, the tangent is going to end up, if you divide it, it's going to end up being minus 1 over root 3. So you could go through and divide each of these values, and we're never looking at stuff in quadrant 3. So it's only the first 3 quadrants. And once you've divided them for one of the quadrants, you can easily say what the other ones are, right? So if I did this like last division here, this one would end up being minus 1 over root 3. And so then those are going to be the same on these other quadrants, right? So this one's going to be 1 over root 3. Here the tangent will be 1. Here the tangent will be root 3. And then those are the only 2 quadrants we ever look for the tangent, so I don't even have to divide the other quadrant. So you can go through and do that division. I should have done it here on the x at 0 radians. So 0 divided by 1 is 0. So these green numbers here that I just kind of put in, these are the values of the tangent at those particular places. So I'm looking for where the tangent is -1. The tangent is -1 here, okay? Usually we'd think of it as 7 pi over 4, but we have to write it as the negative. So our answer here is going to be minus pi over 4. Questions? No. Okay. So F, the inverse cosecant of -1 so remember this is equal to theta, so we're saying that the cosecant of theta is equal to -1. Remember cosecant is 1 over sine, so this would be saying that sine of theta is equal to 1 over -1, or where is the sine of theta equal to -1? Okay, so it is 3 pi over 2, right? So it's here 3 pi over 2, but remember we have to go this way. So rather than write it as 3 pi over 2, we're going to write it as minus pi over 2. I should have boxed these. No problem. All right, I got one more here. So inverse tangent of root 3 over 3. So again, this is equal to theta. So we're looking for where is the tangent of theta equal to root 3 over 3. So you might go, again, Dr. Gorman, that doesn't happen anywhere. I can get root 3 or I have 1 over root 3. Remember that 1 over root 3, if I were to rationalize this, if I multiply top and bottom by root 3 over root 3, this would turn into root 3 over 3. So the answer is going to be pi over 6. Questions? Sure, yeah. So it's pi over 6 because, I'm going to slide sideways here, so that I kind of have some room. So we're looking for root 3 over 3, right? So first off, it's definitely not this, right? Because that's just a plain old root 3, not root 3 over 3. So my only other contender is really this one. So hopefully that turns out to be the same thing. So if you were to take 1 over root 3 and rationalize it, multiply the top and bottom by root 3 over root 3. So I haven't changed my problem at all because I've multiplied by this like thing that looks like 1. And now on the top, I would end up with root 3, and on the bottom, square root of 3 times square root of 3 is just 3. So 1 over root 3 is the same as root 3 over 3. No problem. Other questions? No. Okay. So I know that we have 15 minutes left of class. However, the stuff that I want to do next is about us combining and doing composition and stuff like that with these inverse functions. And it's going to take us a little bit longer than 15 minutes to kind of build it up and do it. Also, like, as opposed to most classes where we have like 20 some people in class, there's actually only 12 of you guys today. And that tends to happen in the class after a test. People think, oh, it's a class after a test. She's going to go over a test. She's not going to teach anything new, which is not true. And so hopefully if you're watching the video, now you know I taught brand new stuff today. But I would prefer to like kind of have a couple more people here in class. And I did budget more than one day for this section. So we got through stuff a little bit faster today than I thought we would, or that we generally do. So why don't we stop here for the day? If anybody has any other questions, no extra credit. Nice try though. If anyone has any other questions, you guys can stick around and ask me. Otherwise, you can do some of the homework for next week. So if you want to go in and start practicing the ones that look like these, then you can do that. And then we're going to do ones where you have like multiple like a trig function, inverse one and stuff. Yeah. Okay. So where we choose, so I'll answer that. So I got a question and people saying, I'm still not sure how you choose which quadrants. So it comes down to this chart. So this chart is, mathematicians have defined it. We define that we are going to look for inverse trig. If we have an inverse sine, we're going to look in quadrants 1 and 4. If we have an inverse cosine, we're going to look in quadrants 1 and 2. If we have an inverse tangent, we're going to look in quadrants 1 and 4. Inverse cosecant, 1 and 4. Inverse secant, 1 and 2. Inverse cotangent, 1 and 2. And those came from when we had to kind of restrict our functions to make them 1-to-1. And so there's lots of choices you could do in terms of what quadrants you pick. Like, it wouldn't have to be 1 and 4. You could pick 1 and 3 for the inverse sine if you wanted to. But mathematicians, we sat down and we said, okay, we want a standard way we're going to do this. The standard is we're going to look in quadrants 1 and 4. So it's how it's defined. It's like literally I'm giving you a definition that the inverse sine, you're looking in quadrants 1 and 4. So these are the quadrants that you have to look out for. And so that's why then all of these, if you notice, all of the blue ones, right? The blue ones all were coming from quadrants 1 and 2 because it was an inverse cosine and an inverse secant. The inverse sine, inverse tangent, inverse cosecant, inverse tangent, they were coming from 1 and 4. Does that help? No problem. Any other questions? Yeah, so as soon as I get them graded, they will be in, so they should happen before class on Monday. So they'll probably happen sometime over the weekend. Nice try, but no. You get the reward of you got to be here and ask me questions and see me teach the material. Right? That's extra credit enough. No problem. You too. Have a good one. Yep, that's fine. It's not that you have to memorize the whole chart. You just have to know what quadrants to go to. So as long as you know which quadrants to go to, that's all that really matters.